Here we have the chemical equation of methane plus oxygen forms CO2 and water in two different forms. We have the chemical equation, and then we have the reaction coordinate diagram. So we can see that we have our products, our methane and our O2, and our reactants, our CO2 and our H2O. And we've plotted them as a function of their energy. And we can assume that the energy, in this case, mostly comes from the enthalpy. Now, we talked about how in order for the reaction to progress, so for methane and oxygen to become CO2 and H2O, they must first form a transition state or an activated complex, which is high in energy, before they eventually can become the products. And the energy difference between the reactants and the activated state is our activation energy, or our E sub A. So let's say we have our situation where our E sub A is equal to 188 kilojoules. We also mentioned previously that the difference between our products and our reactants would be the delta H. And in this case, our delta H would be equal to negative 800 kilojoules. So we can draw this out, make a nice little smooth line there. So we know that the reaction rate of our reaction is related to the height of that energy or enthalpy barrier that the products or the reactants have to cross to form the transition state before they can become the products. So the bigger the EA, or the steeper the hill, the smaller the reaction rate, and vice versa. However, when we were thinking about this from the perspective of the reactants going to the products, but it turns out that we can also think about the reverse reaction. So the EA that we see here is the EA of our forward reaction, but the energy difference, or that enthalpy difference between our products and our transition state, is the activation energy for the reverse reaction, or the EA sub R. And so we have these two reactions that are going on, and they represent two different halves or sides of a chemical equation. So in our discussion of kinetics, we've looked at this simplistic reaction a lot. If we have A going to form B, the rate of the reaction is equal to the rate constant times the concentration of A, assuming that this is a first order reaction. However, what we've neglected is that there's also a reverse reaction. B can go back to form A, and the rate of this reverse reaction is equal to a different rate constant times the concentration of B. If we combine these two together, we have a situation where our reactants and products can interconvert between each other. And we can use our rate laws from those two separate equations to write it out. So in our chemical reaction, we have the forward reaction where the rate of that forward reaction is equal to the rate constant times the concentration of A, whereas for the reverse reaction, the rate is equal to the rate constant for the reverse reaction times B. So ultimately, our forward reaction is going to be working to make B, whereas our reverse reaction is going to be working to make A. Ultimately, it's a battle between the forward and reverse reaction, and with the conclusion or decision of who is faster. So if we look back at our reaction up here at the top, we notice that our EA is smaller going from our reactants to our transition state than going from the products to the transition state. So our forward reaction with that smaller activation energy has a higher rate than the reverse reaction. So that's why the forward reaction in this case wins. And this comes from our relationship here, where the rate constant, or the rate of our reaction, or the rate constant of the reaction, K, will be equal to our constant A times e to the negative EA over RT. So an increasing EA leads to a smaller K. Now, while one of these reactions may dominate or be the winner, neither of those reactions will ever stop. In this case, for our A to B, if our KR is slower, that reaction will keep going. It'll just keep going, and it'll keep going as long as B exists. It'll just go slowly. And at this point, we will reach an equilibrium. And so at equilibrium, we have a situation where the rate constant of the forward reaction times the concentration of our reactants is equal to the rate constant of the reverse reaction times the concentration of our products. So these two must be equal to each other, or the rate of the forward reaction is equal to the rate of the reverse reaction. And so if we have a situation like we saw with our methane, if we have a big rate constant for our forward reaction and a small rate constant for our reverse reaction, to make sure that these sides of these equations stay equal to each other, we'll have to have a small concentration of A and a large concentration of B. And so ultimately, the concentration of A and B are going to modulate K, so both sides of our equation, or the rates for the forward and the reverse reaction, will balance each other out. And ultimately, we're heading towards chemical equilibrium, where the rate of the forward reaction equals the rate of the reverse reaction. Now, if we really are at equality, we can do some really cool things that can tell us about the state of the reaction. So, if we have the Kf times A is equal to Kr times B, if we set the ratio of the rates equal to the ratio of the products and the reactants, now we can use the ratio of the rates to tell us something about the ratio of our concentrations. So if Kf over Kr is equal to 1, then the concentration of B is equal to the concentration of A at equilibrium. If Kf over Kr is greater than 1, then B must be greater than A at equilibrium. And finally, if Kf over Kr is less than 1, then the concentration of B must be less than the concentration of A at equilibrium. And in this case, when B is equal to A at equilibrium, neither of our products or reactants are favored. But if we find ourselves in a situation where Kf over Kr is greater than 1 or B is greater than A, this means our products are favored at equilibrium. So we're going to have more products at equilibrium. If we have the opposite case, this means our reactants are favored at equilibrium. So ultimately, this Kf over Kr relationship was so important that we gave it its own abbreviation, big K, or KEQ, and it has the name equilibrium constant. And ultimately, if we have a reaction that's at chemical equilibrium, the magnitude of the equilibrium constant, or K, tells us how much one side is favored over the other.